Hello, my name is Gonzalez Garcia. I'm a current student at the University of Bath. And in this video, I'm going to talk about a work called Asymptotic Moments of Spatial Branching Processes. This is a joint work with Emma Horton and Andreas Cipriani. So let me start by defining what a PG Markov process is. So we consider a spatial branching process in which particles evolve independently according to a P Markov process where P is a semigroup on a Lucent space E. So in an event of branching, particles die at certain rates, beta, and new particles are created instantaneously in this space. So the configuration is described by a random counting measure set of A and with probabilities P sub x and Ex. We also define the so-called branching mechanism to be the one described in equation 1. And on the event that the process has not become extinct or exploded, this process is Markovian in the space of integer atomic measures. So in this representation, xt is going to be the sum over from 1 to nt of these atomic measures on the positions of the particles. And nt denotes the number of particles alive at time t. Now, this branching mechanism also is known as non-local branching mechanism. Now, a P psi phi superprocess is a Markov process with a stated space M of E, where M of E denotes the space of local finite measures on the space E. And this is called a superprocess if it has transition semigroup E, satisfying equation 2, where the V in the right-hand side of equation 2 is a semigroup evolution that is characterized via the unique bounded positive solution to the evolution equations shown below. So now looking at this evolution equation, a psi is normally called the local branching mechanism, which has this Levy-Ching representation, and psi is called the non-local branching mechanism with that representation. So our main results concern understanding the growth of the kth moment functional in time. So this is the expected value of the integral of f against t process x, all raised to the power k. And it's going to be denoted by t sub t super index k. So the objective is to show that for k bigger or equal than 2 and any positive bounded measurable function, the following limit holds, with g being a scaling factor that depends on time, and the constant can be identified explicitly in both branching Markov process and super process case. So for this result, we need basically two main assumptions, the one of them being a Perron-Frobenius type that states that there exists an eigenvalue or a leading eigenvalue lambda and the corresponding right eigenfunction and finite length eigenmeasure. So these two functions, and well, this eigenfunction and left eigenmeasure are going to appear in this constant C mentioned before. So the Perron-Frobenius assumption states that if we define the quantity delta t to be the difference between the semigroup scaled by e to the minus lambda t and the integral of f against the left eigenmeasure, this quantity is finite and it's going to go to 0. The second assumption, it's a moment condition on the offspring distribution, particularly for a branching Markov process. This states that the kth moment of the number of offspring is finite. And in the case of the super process, the condition is that these two integrals are finite. And recall that they are related to the local and non-local branching mechanism. So as the main result, we have in the critical case where lambda is equal to 0, lambda the leading eigenvalue, it states that if we define now this quantity, the difference between the kth moment scaled by a factor of t to the minus k minus 1, this will converge to the constant on the right-hand side of this difference, where the v shown can be explicitly found in both branching Markov process and superprocess cases. So in short, subject to these two assumptions, we have that for a bounded positive function, the scale limit of the kth moment by scaled by t to the minus k minus 1 is equal to a constant. So it means that at criticality, the kth moment scales like t to the k minus 1. So briefly, an idea of the proof is that, well, the main idea is to study the nonlinear semigroup, which is the expectation of the quantity e to the minus some theta times the integral of f against x associated with the process. So now, using this, the following relation shown in equation 6, we can read it as the, when in equation 6, we see that the kth moment is minus 1 to the k times the kth derivative of this nonlinear semigroup. So this means that we can use knowledge of the nonlinear semigroup to study moments of the process. And actually, the first step of this proof is to write an evolution equation for this nonlinear semigroup in terms of the linear semigroup of T. So now let me just comment that this is a very generic approach, but despite that, the proof of each of the two processes, branching Markov process and superprocess, requires slightly different technicalities due to the fact that on the one hand, superprocesses have Levikin-Chain branching mechanisms, but no particles. Whereas on the other hand, branching particle systems do have individual particles, but less regular branching mechanisms. So due to this discrepancy, to compute the derivatives for the branching particle systems, we use the Leibniz rule. And in the case of superprocesses, we use a Faddy-Brunos rule. Now, for the non-critical cases, we have some other results that present a significantly different picture for the in these cases. So for these settings, the exponential behavior of the first moment semigroup becomes a dominant feature of the higher expected moments. So for example, in the supercritical case in which lambda is positive, now the kth moment scales now like e to the lambda kt. That is the first moment to the power k. But in the subcritical case, the kth moment scales like e to the lambda t. That is the first moment. In these two last slides, I'm showing just the limits for the branching Markov process case because the superprocess have a different, a bit longer expression, but both cases are scaled by the same factor on time. Thank you very much.